Hello there guys, welcome to this video where we're going to be taking a look at this really cool integral right here with a flow function in the bottom, which is really interesting. So let's get right into it. So to start off with, let's define what we mean by the flow function. I'll give you the mathematical definition and then we can kind of intuitively talk about it. So the flow of x is equal to n, okay, it's equal to n given that x is between n and n plus 1. And also n is an integer. So it's quite a simple definition right there. So it's kind of really understand this definition. Let's look at a few examples. So the flow function of negative 1.5 is going to be equal to, well, negative 1.5, it's between negative 2 and negative 1. So it's going to be equal to negative 2. Okay. I think that's a bit of a hard example to start off with. You know, if we're given any simple number like 28.2, okay, that's quite simple. It's just 28. Okay, so it's the leftmost integer to x, basically. So now, how can we go about doing this integral? Well, this definition is our biggest superpower in working this integral out, because we know that this flow function here is equal to n whenever x is between n and n plus 1. So what we can do is a very clever thing, which is to split this integral up into a bunch of different integrals. So how we're going to do that is, let's say the first integral, we're going to sum from 1 to 2. Okay? And I'm not going to write what's in between yet. Maybe you guys have already guessed it. The second integral, I'm going to sum from 2 to 3. And then third integral, I'm going to sum from 3 to 4. And then the fourth integral from 4 to 5. Okay, and so on and so forth. You know, all the way off to infinity. Now, what does this mean? Well, what this means is this, on each of these different intervals, this floor function of x is just going to be equal to this lower bound, right? Because in this integral here, the floor of x is bounded between 1 and 2. Okay, bounded between 1 and 2. Now, what does that mean? Well, if x is bounded between n and n plus 1, the floor of x is just equal to n. So it's pretty much just going to be equal to 1 in this case. So all we're doing is dx. And then in this integral here, it's just going to be equal to 2. So we have a quarter dx. Okay, and then it's going to be equal to 1 over 3 squared, which is a 9th dx. And then it's going to be equal to 1 over 4 squared, so a 16th dx, and so on and so forth. Okay, so now, obviously, we don't want to be integrating an infinite number of integrals here. So let's kind of condense this down, okay? So each of these terms are being integrated from n to n plus 1. So essentially, two numbers that are consecutive. Okay, so what we can do is we can say, well, it's integrated from n to n plus 1. Okay, the function is just 1 divided by the flow function of x squared, but then the flow function just becomes the lower bound. You know, here it was 2 squared, 3 squared, 4 squared, obviously 1 squared, but then 1 over 1 squared is 1. So what we can do is, well, we can say that the inside is just 1 over n squared dx, right? So we can literally say it's 1 over n squared dx. But then, well, we have a bunch of integrals here that we're summing up. But in the bottom here, we just have 1. So what we can do to deal with that is just take a summation. So just take a summation here from n equals 1 to infinity. And voila, we have our integral. And now this is a very standard kind of calculation right here. Because, well, as we can see, what that's going to equal, let's take this integral here apart. Okay, so that's the integral from n to n plus 1 of 1 over n squared dx. Well, that's going to be equal to x over n squared, because in the x world, 1 over n squared is just a constant. So x times the constant using the power rule from n to n plus 1, which is simply just n plus 1 over n squared minus n over n squared, which is going to be equal to 1 over n squared. Okay, perfect. This integral is equal to 1 over n squared. Amazing. So let's gather it up with the summation that we have. So we're summing from n equals 1 to infinity 1 over n squared. And most of you guys hopefully would know that this is equal to pi squared by 6. It is the famous Basel problem. Amazing. So this integral here is pretty much just pi squared by 6. How awesome is that, guys? So thank you very much for watching this video, guys, and I'll see you guys in the next video.